Okay, so our objective today is actually to solve a few questions similar to the ones that you have in your assignment as a tutorial. One thing that I put a notice on here is this page is actually, I remind you to go to this website. I remind you to go to this website and try to solve all the problems there, okay? And remember, I asked you to do this a while ago, and I told you if you have any questions, come back to me. Nobody came back to me, which means to me that nobody actually tried. So please go and try to solve the questions here. And you have in that interactive website enough help and hints that should enable you to do this without a tutorial from my side. I might actually visit the website and give a couple of quick tutorials there. But generally speaking, if time does not allow, I'm not gonna do it, okay? So anyways, it says here, this problem that in a cellular network, which have packets that have an average length of 32 bytes. And so this is L, the packet length, right? L. And packets are arriving on an average rate of 10,000 packets per second. So this is something called lambda, the arrival rate. And the average transmission rate of this is the data transmission rate, of the system is 54 megabits per second. So that's R, the transmission rate. The average distance between any node and the base station is 1 kilometer, so we call this D, the distance between one node and the base station, right? So this is the distance T over which the signal has to travel with the speed of light c, right? Assume that the speed of light in air and free space is this, so that's c. Packets are stored in the base station memory for an average time of 10 microseconds per packet. So this is delay of queuing, right? This number. And the base station takes about 15 microseconds to process each packet. So this is what we called the processing delay, DP, okay? What's the average packet transmission delay? So D transmission is defined as the packet length, right, in bits, so L in bits, right, divided by R in bits per second, okay? So that is equal to 32 times 8, that's the packet length in bits, divided by transmission rate is 54 mega, so times 1024 times 1024 megabits per second, okay? And in this case, you can calculate the values, okay? And the next question says, what is the packet propagation delay? So remember the DP, let's call it DR, the propagation delay, is equal to the distance, D, divided by the speed of propagation, C in this case. So how long it takes the packet since it comes out of here until it reaches here. That's called propagation delay, right? So that is equal to 1,000 because it's in meters. So it's 1 kilometer, right? The distance D divided by C, which is 3 times 10 to the power 8, right? And that will give you the propagation delay. What's the total average delay experienced by a packet between the cell phone and the base station? So D total total packet delay is equal to dequeuing plus deprocessing plus depropagation plus detransmission, right? So the sum of all these numbers, which we have calculated already, some of them are already given to us, the DQ and the deprocessing, right? And there is one that we calculated here, another one that we calculated here. So you just add them together. What's the throughput of this system in bits per second? So for a particular system, the whole system, right, we have an average input to the system and an average output from the system. And the throughput is typically, right, call it THR, is equal to the minimum of, let me write it in a more spacious area. So the throughput of a system, by definition, the number of successfully transmitted packets per second, bits per second, okay? So in this case, it's gonna be the minimum amongst the input rate, so R input, and the output rate, R output. So the minimum of R input, R output. Okay, which one is less? And in this case, what's the rate of input to the system? We have 10,000 packets, but we need to calculate all of this in bits per second, right? Bits per second, bits per second. And the throughput is bits per second, okay? So this is, we have 10,000 packets arriving per second, but the packet includes 32 times 8 bits. So we have the input here, 32 times 8 times 10,000, right? That's the rate at the input. The rate at the output is the 54 megabits per second. So it's 54 times 1024 times 1024. Okay? So which one is less? And then this will give you directly the throughput. Okay. Next problem on graph theory. So looking at this graph that we see here, the first question says, is the graph G complete? And a complete graph is defined as a graph where every single vertex has an edge to every other vertex in the graph, right? For example, just a quick example here, we see that this vertex and this vertex, they are not connected directly. So this graph is not complete. So the answer is no. And a counter example, to prove something false, you just need to show an example that it is false. To prove something true for all cases, you have to have a generalized proof. So here we just need to show a case. So no, and a counter example, okay, to being complete is vertex 6 has no edge to vertex 4. For example, just one example is enough. Is the graph G connected? We can see that starting at any point in this undirected graph, we can reach every other point. Then the answer here is yes, because from any vertex, we can reach any other vertex by traversing edges. Okay, what's the total sum of degree of the graph G? So we can go across each one of those vertices and add the degrees. So we have 3 here, plus 2, that's 5, plus 4, that's 9, plus 3, that's 12, plus 2, 14. So to 6, right? The sum of the degrees of the different vertices, we found it to be 14, right? And we could have found this also by saying what? There is a theory that says that this sum is also equal to 2 times the number of edges, right? And we know here that we have 7 edges. So we know that this sum is equal to 14, right? So that's another way to do it, okay? Using that theorem that we... Okay, consider the following network of servers represented as a directed graph G, okay? And the network of servers represented as a directed graph G, where the vertices represent servers. So all these vertices S1, S2, S3, S4 are servers, and the edges represent directed data links with the associated cost, right? In this case, the cost represents latency, delay, okay? Is server S4 reachable from server S1? Can I start at S1 and respect the directivity of the graph and reach S4? Yes, I can. One example for this is that I can do this. There are many other ways. So the answer here is yes. Then it says, if yes, list all possible directed paths from S1 to S4. So let's see those directed paths from S1 to S4. Okay, so there is one path that goes this way, right? There is another path that goes this way. So here, 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 right? There is a third path that goes this way. So up, go down. Do we have any other path from S1 to S4? Yeah, we have the direct from S1 to S4. This is also the direct path, right? So we go here. Okay. Okay. So if we want to list these paths, we are going to say, and so the answer is yes, and the paths are S1, S4. That's one path. The other path is S1, S2, S4. Third path is S1, S2, S3, S4. Right. Okay. Using the Kestra algorithm, find the shortest path, minimum total latency, from S1 to all other servers, right? Show the state of the algorithm at each iteration. I'm not gonna do this because it's gonna take a long time, but I'm just gonna do a first few steps similar to what we did before. So the first state is gonna be inspecting the first step. So first graph that we will have is gonna be this line, right? At a cost of 6. So this point is gonna be reachable with a value 6 from S1. And this is gonna be reachable with a value 10 from from S1, right? That's first state. And then go to the second state where I start inspecting some of these guys, right? More. So in the second state, I would see that, right? I have let's inspect first the upper one. So this guy, let's inspect this one first. So we see that I still reach it by the 6. So the 6 still exists. The cost of this is 6, right? But then I can use this link to reach this guy, and the cost in that case is 6 plus 5, that's 11. So actually, no, I stay with this as my reachability. Okay, and now I can reach also S3. So I have this. Okay, and it's gonna be 7, the cost to reach here, right? Then next step is from S1 right? So now I'm gonna inspect this guy to see what's gonna happen from here. So I can see that if I inspect, so I still have, this is not gonna be affected. I still have this as my direct link here. And the cost of this is still 6, right? Now the connection from here to here give me a 7. If I try the other one, which is coming from, so this give me a 7, right? Now I'm inspecting what happens here, right? So I come here, and then that's 10 plus 2, 12. So it's not gonna change that. And there's no other way to go from here. So even after inspecting this, I stay with, so here, S1 is my inspected point. Here I'm inspecting S2, checking where can I go from S2. Here I'm checking where I can go from S4, right? And nothing changed when I inspected that. Everything stayed the same. So I still reach here with 10. I still reach here with 7. Now I'm gonna inspect S3. Now let's put those guys, actually, okay. And let's go through what we can do here. So again, stopping at this point, S3, I can see that from it, I can go this way, which is 5, and then add a 10, so 7 plus 5 plus 10, that's too much. So this stays as 10, right? So after that, we will see that the shortest path here is this guy. So stays the same, right? And give me a cost of 6. I can reach this through this path. It gives me a cost of 10. And I can reach this through this path. And the cost is 7. And now I have all the shortest paths. So I can reach here with 6. I can reach here with 7. I can reach here with 10. These are the shortest paths. Is this graph strongly connected? The answer is no. Because, for example, oh yeah, it is. So the answer is yes, actually. Because if I start here, I can reach all these. We already tested that. If I start here, I can reach S1 through this path. I can reach S2, S3, I can reach S4. If I start at S3, I can reach S1, I can reach S2, I can reach S3. Yeah, so if I start at S4, I can reach S3, and I can reach S1, and I can reach S2. So yes, and it's connected through. Write the adjacency matrix for this directed graph. So we have S1, let's see. So 0. We don't have loops, right? And then let's start. From S1 to S2, I have an adjacency. From S1 to S3, I don't have an adjacency. From S1 to S4, I have an adjacency. From S2 to S1, I don't have an adjacency. S2 to S3, I have a 1. S2 to S4, I have a 1. From S3, I can reach S1, so there is an adjacency, this line, right? From S3 to S2, nothing. It's only coming, it's not going. And from S3 to S4, nothing. Last, from S4 to S1, I can't. From S4 to S2, there is no direct link. Only coming from S4 to S3, there is a 1. Thank you. Okay. A delivery drone must fly along every direct route in a warehouse district exactly once. A district layout is modeled as the following undirected graph, the one that we see right there, okay? Where vertices represent the warehouse, right? So these vertices are the warehouses, and the edges represent flight corridors. So these are the different connections. So you can do directly from this warehouse to this warehouse, or from this to this, and so on, right? The first part right here, determine the degree of each vertex. Does this graph have an Euler circuit? Justify your answer using the relevant theorem. So first part is determine the degree of each vertex. So let's do that. So degree, so degree of vertex W1. So degree, sorry, writing was white. So degree of W1 equals 3. Degree of W2 equals 3. Degree of W3 equals 3. Degree of W4 is equal to 2. It's 1. Degree of W5 equals 1, 2, 3, 4, 5. And degree of W6 equals 2. Right, so these are the degrees of the different vertices. It's the first part. And the second part says, does the graph have an Euler circuit? So again, what was the theorem? The theorem says that a graph will have an Euler circuit if and only if is connected. So you can get from any vertex to any vertex. We can see that the graph that we have here is connected. You can start at any vertex and go across some edges to reach any other vertex, right? It's not fully connected, but it is connected. That's part of the theorem. And then the second condition of the theorem is that all the vertices do not have odd degree. Now we can see that several vertices here have odd degree. So the answer to the Euler circuit question is going to be no, because some vertices have odd degree, right? And the theorem says if and only if, right? And we have many examples. So vertex W1, vertex W2, vertex W5, vertex W3, all of these have odd degrees. Does this graph have an Euler path? Now that's a different story. So can we do that? I mean, we have more than, so the answer to that question is going to be also no. And the reason is if you pick any of the odd, so when would a graph have an Euler path? If you can start from an odd, finish at an odd degree, right? And then all the other vertices are with even. But this is not possible because if I start here and finish here, I will have some of the others. If I start here, finish here, I will have some of the others, and so on. So if I pick any odd start point and end point, I will still have too few other odd degree vertices, right? This would have been only possible if we have only two odd degree vertices and then you start and you finish at those ones. But right now, we cannot really have an Euler path in this graph. So the answer is no. And the reason is because if we pick start and end vertices with odd degree, right? The remaining vertices will still have some with odd degree. So no. Okay. Now let's go to part C. It says that the drone, so you have that drone, is also needed to stop at each warehouse exactly once, right? To pick a package or to deliver a package. Here to pick a package. Does a Hamiltonian path exist? So that means that it can start at one of the vertices and then it can go across all the other vertices exactly once, right? So the question is, does a Hamiltonian path exist? And yeah, I mean, we can immediately find one. For example, I can start here, right, at W1, W4, W5, W6, W3, W2. So that's one possibility. And the question says find one, so we just found one, right? And you can have, I'll give you some other examples. So let's look at this one. You can start, for example, at this guy, right? and then go over here, over here, over here, over here, over here, right? That's another Hamiltonian path, right? So the answer is yes. And I've shown you some examples, right? Shown you 2 examples. There might be more actually. Okay, but that's enough. Does a Hamiltonian circuit exist? Visit every warehouse exactly once and then return to where you started. And the question is yes, right? Remember, there were a couple of theorems for Hamiltonian circuits. So one of them says that if you have n vertices, then for each vertex will have a degree greater than or equal to n over 2. Of course, here we have 6, but some of the vertices have 2 degrees of 2, so that theorem is not very useful. Remember, that theorem is not f and only f. It's just an f. So if the theorem is true, then we can find the Hamiltonian circuit. If the theorem is false, we don't know. In this case, the theorem is false, so it doesn't really give us a definitive answer. There was another theorem that says for any 2 selected vertices, if you add their degree, the sum of their degrees actually adds up to some number greater than or equal to n, the total number of the vertices. And again, I can show that this theorem is not true. For example, if I pick this vertex and this vertex, because this is of degree 2, this is of degree 2, adding them together will give me 4, which is not actually 6. So that theorem also is not useful. So my only way here is to find the circuit, right? But then we know that if we found a Hamiltonian path, right, and the 2 ends of that path are adjacent, then we know that we can find the Hamiltonian circle. And this is the case that we see here. So actually, this path that we selected with red color can be converted into a Hamiltonian circle, right? So you start here and you finish here, that's the path. And then the start and the end point are actually adjacent because they have an edge connecting them, then you can close the circle, right? So the answer here is yes. And the reason is because it has, right, a Hamiltonian path where the start and end vertices are adjacent. So this means we can convert this path to a circle. Or it would suffice in this case to say yes, and the reason for that is that I can find one. So that answers also the question, because you can just show that there is one, and then the answer would be yes, okay? And you will list that one. Okay, so that's it. Reminder that in addition to these problems that we have solved here, please, please, please go to the online resource that I mentioned earlier and try to solve all the problems. Try to solve all the problems. And if you have a question, come back to me. Okay, good luck.